These are the rotational second law problems, the toolkit for it. So this is the toolkit for the rotational second law problems. Please pause this page so that you can write these down. We'll apply the rotational toolkit problem to this problem here. It says derive an expression for the acceleration of a flat disk of mass m and radius r that rolls without slipping down a ramp of angle theta. So the first thing is to draw a force diagram and a motion map. So let's start off with a force diagram. Oops. So let's start off with that force diagram. It would look like this. So there's an incline. There will be a normal force pointing up like that. A force due to gravity that we'll call mg. The normal force we'll call n. And a force of friction that would be actually applied here like that. And let me use a different color pen to highlight the fact that the radius r is right there. Let's actually also look at the components of the force due to gravity. There's this vertical component and there's this horizontal component. So we drew our force diagram. Let's also include a motion map. So we'll assume it starts with no velocity and picks up velocity on the way down the hill, so, or the incline, so the acceleration would also be in that direction. So there's our force diagram, there's our motion map. We're drawing the force diagram with components, so we've included that already. This component here would be mg sine theta. Okay, and we could also rotate that, but at this time we're going to choose not to. We're going to determine the coordinate system now. So the coordinate system is important because we want to make sure that we are going to determine which way is positive. So let's call this direction right here positive. The next step is to explicitly write out the sum of the forces equals ma. So we'll actually just write that out. The sum of the forces equals ma. And we'll also explicitly write out that the sum of the torques, let me rewrite that. Now this is important for the AP test because we want to make sure we let the graders know that we know these facts. The sum of the torques equals 0. Oh, I'm sorry. The sum of the torques equals ma. So we want to explicitly write those out. Now we want to write out Newton's second law equation for each rigid body. Okay, so I've got my rigid body there, and I'm only going to need one equation because I only have one rigid body. So the equation, and we'll just look at the horizontal version of it, will be this. So for the block there, our sum of the forces equals ma equation will be mg sine theta, that's in the positive direction, minus the friction, which I forgot to label here. This is the friction right here, minus f is equal to ma. It says also write the second law equations for each object, and for the system. Oh, okay. The first thing, the rigid body, that was the sum of the torques equation. So right here, let's do that now. This part right here, let's write that out. This part right here, the rigid body part. That would be this equation. Okay, so we're going to call this equation, because I got I got the sum of the torques equaling ma. I know that there's only one torque, and that's due to the friction. And that torque let me actually rewrite that. The torque is equal to ma. By definition, the torque is the force times the lever arm. So the force of friction is providing a torque in that direction, and we're going to multiply that times the radius to calculate out the torque. We know from the second law, okay, and actually we wrote those out wrong, so let's rewrite that. Let's erase this. That shouldn't be ma. That should be I. That should be I alpha. And so should that. Let's erase that as well. So that should be I alpha. I in this case, we know that because we've got a disk, I is equal to 1/2 mr squared. So this is going to be 1/2 mr squared alpha. Okay, so here's our equation for the forces, and here's our equation for the torques. There's only one torque. Let's look specifically at our torque equation. So we're at the last step where we're going to substitute numerical values where appropriate and solve for unknowns. Now notice I can cancel out one of these r's. Okay, so I get F is equal to 1/2 mr alpha. But because it's not slipping, we can also say that the acceleration is equal to r alpha. Okay, now this is an important equation to know because I can plug that into r alpha and I get the equation F is equal to 1/2 ma. Over on this other side, let me choose a different colored pen. Over on this other side, I know that because this F is equal to 1/2 ma, I can plug that into this equation there, and I would end up with mg sine theta minus 1/2 ma is equal to ma. If I add the 1/2 ma to both sides, I get mg sine theta is equal to 3/2 a, and therefore a would be equal to 2/3 g sine theta. So there's my equation for the acceleration. The next problem we want to look at is this pulley problem, where it also asks us to calculate the acceleration, and it says assume the pulley has mass m1 and radius r and is a uniform disk. So first thing we'll do is we're going to draw our force diagrams. So let's do that. Let's do it actually on these objects. So on M2, I've got a normal force pointing up. I've got a force of tension pointing along the string. We'll call that T2. And we have the force due to gravity, M2G. Likewise, on M1, I've got M1G. And upward, I have T1. The forces on my rotating object on this pulley are T1 in this direction and T2 in this direction. I also know that the radius of this is R, so I can label that R for that lever arm and R for that lever arm. So I've got my force diagram. Now I want to draw in my motion map. So I know that in this direction I'm going to start off with no velocity, and it increases velocity to the right. So I know my acceleration should be constant but to the right. For this other object, I've got no velocity at the beginning, but it's picking up speed downward. So my acceleration will be downward for this object. We don't need to rotate anything. We have no components, so we can skip the second step. The third step is determine the coordinate system. Well, the coordinate system, I want to say in this direction here, is going to be positive. So for all three objects, to the right for M2, clockwise for the pulley, and downward for M1 will be positive. So we determine our coordinate system. Our next step is to explicitly write out Newton's second law. So really important step there. Let me get a different colored pen here. We want to explicitly write out that the sum of the forces equals MA. And we also want to write out that the sum of the torques equals I alpha. So those are essentially Newton's second law in the translational version, I guess, of Newton's second law, and the rotational version of Newton's second law. Now, let's write out the equations. Let's start off with the pulley and write out its equations. So, for the pulley, we're going to say that the sum of the torques equals I alpha. We've got two torques. We've got a torque due to T1 and a torque due to T2. The torque due to T1 would be T1 times its lever arm, which will be R. And that's in what we're going to call the clockwise direction. And normally clockwise is negative, but because this direction is now positive, we will call it positive in this case. So T1R, the other torque T2R is negative. It's the counterclockwise one. And because this is a pulley, I'm going to say that it's equal to 1/2 m r squared. That's this part, the I. Then alpha, which is that part right there of that equation. So in simplifying this, we can cancel out these r's squared there. We remember again that the tangential acceleration is equal to r alpha. So this equation essentially becomes T1 minus T2 is equal to 1/2 MA. So that is my equation for the rotational version of Newton's second law. So that I have some more space, I'm going to take this equation, the linear version or the translational version of Newton's second law, and I'm going to show the work over here. Again, we start off with the sum of the forces equals MA. Now, I'm going to look at this as a system. So let's write out the system equation. So the first force I'm going to look at is M1G. It's downward for that object, and we decided downward there would be positive. So that's going to be a positive M1G minus its torque of T1. Okay, and then we'll skip on up here to T2. It's a positive T2 because it's moving to the right. And I'm going to set that equal to the two masses, M1 plus M2A. So that is the expanded version of Newton's second law, the translational version of it. Now, this is the system equation for the pulley. What I want to do is also to write out the equation for each object, because we never know when that might be helpful for us. So over here on the side, I'm going to write out the equation for M1. The equation for M1 would just be M1G minus T1 is equal to M1A. And the equation for M2 would simply be T2 is equal to M2A. So these are the equations for M1 and M2 individually. And the reason, again, we do that is just in case we'll need that for later on. Now, if I combine the system equation with the torque equation, I notice that I've got something very similar here with the negative T1 plus T2 and the negative and the T1 minus T2 there. So if I just change the signs here and I make this minus T1 plus T2, this will equal negative 1/2 MA. And then what I can do is I can take that equation and I can plug it into the other equation by simply taking this section of it and plugging it into there. So my new equation, after substituting this, I would get M1G and I would have a minus 1/2 MA for my substitution, and that would equal M1 plus M2 times A. And if I combine like terms on the left hand side, I would have M1G equaling M1 plus M2 plus 1/2 MA. And if I multiply, let me put the parentheses around that. And if I divide both sides by things in the parentheses, I would end up with M1G all over M1 plus M2 plus 1/2 big M. So this would be my equation for the acceleration of the system. One final version is this one here. This says, what is the acceleration of this system? The magnitude of the tensions are T1 and T2. Assume the surface is frictionless and the pulley has a rotational inertia of a uniform disk. So again, we want to start off with our force diagrams. So with our force diagrams, we would have on T2, we would have M2G and T2 upward. Over here we would have the normal force and T1 in the direction of the string that's pulling it, and then M1G. The forces on the pulley, there would be T1 pulling in this direction, and there would be T2 pulling in this direction. We have to remember that the radius, we need the lever arm, so I need that R there, and I'm going to need that R there to calculate the torques. Also, if I look at the components for M1G would be right here. This would be the vertical component, and this would be the horizontal component. And obviously I would be more interested in that horizontal component, which would be M1G sine 30 degrees. I'll just call it sine theta, because as we remember from before, this would be the angle theta, and if we were to call this theta. Okay, so we drew the force diagram. We haven't drawn a motion map, so this object, the assumption we'll make is that it's going to go in this direction. So let's also determine the coordinate system. Let's say the coordinate system for this setup is going to go positive in this direction. So therefore our motion map would show that we start off with no velocity and it picks up velocity in this direction. So the acceleration would be constant and downward. For this object, we would say that the velocity would increase up the hill like that. So the acceleration will be constant up the incline. So we've drawn the free body diagram. We've drawn the force diagram with the components. We didn't rotate this. We can if we like to, but we'll just look at it from that point of view. Determine the coordinate system. We've done that. Now we need to once again explicitly write out the sum of the forces equals MA, and the sum of the torques equals I alpha. So the first thing we'll do is we'll look at the sum of the torques. The sum of the torques, once again, equals I alpha. So I've got two torques. We're calling this direction for this T2 positive. So let's call that first torque T2 times R, the lever arm, minus T1 R. And that'll equal I alpha, so it's a disk again, so this part will be 1/2 mr squared times alpha. So that's the part that's the rotational inertia. And once again, we remember that the the tangential acceleration is equal to R times alpha, which is the rotational acceleration. So this equation becomes T2 minus T1, and that will equal 1/2 m times A. For Newton's second law, the translational version of it, the sum of the forces equals MA. Let's look at the system first. So we'll look at the system. Its system equation, we'll take into account, let's take into account this M2G and this T2 first. M2G is in the positive direction according to our coordinate system, so we'll have M2G minus T2. And then for T1, T1's in the positive direction, so we'll say positive T1 and minus M1G sine theta. M1G sine theta. And that's going to equal M2 plus M1 times acceleration. So this is my system equation. Another important thing to do is to also look at these individually. I don't know why that's not erasing. So if we look at these individually, for M1 I would have this equation. For M1 I would have T1 minus M1G sine theta, and that would equal M1A. That's just the equation for just M1 individually. And the equation for M2, would be M2G minus T2. That would equal M2A. So again, we may not necessarily need the equations individually for M1 and M2, but we never know. It depends on what the problem asks us later. So for the time being, we're going to look at the Newton's second law, the expanded version for the torques, and Newton's second law for the translational forces, but as an entire system. So I'm going to combine this equation, T2 minus T1, and I'm going to plug it into there because the negatives, because I've got a negative sign there, because this is positive T2 minus T1, and this is T2 plus T1, and that will make this negative 1/2 MA when I plug it into the equation. So that's M2G minus 1/2 big M times A minus M1G sine theta, and that will equal M2 plus M1A. Again, I don't know what that A is doing there. Okay, so we combine the like terms. So on the left-hand side, I'm going to have M2G minus M1G sine theta. And on the right-hand side, I'm going to add the 1/2 MA. So I'll have M2 plus M1 plus the mass of the pulley, capital M, and all of these times A. So once again, combining like terms, I'm going to factor out the G here, and I've already factored out the A, so solving this for A will give me M2G minus M1G sine theta all over M2 plus M1 plus, well, that should be a 1/2 M, should be a 1/2 there, 1/2 M. And I can also combine like terms in the numerator if I'd like.